Here's the twist. The hardest part of AI-designed, 3D printed space engines is not printing them. It's proving they are safe, inspectable, repeatable, and certifiable every single time. Modern metal printing can already create astonishing internal shapes. Cooling channels can snake through a chamber wall. Manifolds can merge and split inside a solid block. Injectors can be integrated instead of assembled. In principle, this can cut part counts, reduce welds, and remove joints that like to fail. Yet propulsion is unforgiving. A tiny void, a rough internal surface, or a subtle crack starter can turn into a hot spot. Hot spots become burn-through. Burn-through becomes a mission loss. So the near-term constraint is not imagination. It's quality assurance that can keep up with imagination. When geometry becomes complex, inspection becomes the pacing item. If you cannot see it, measure it, and bound the defect population, you cannot certify it. And if you cannot certify it, you cannot fly it on a crewed mission or a very expensive payload. That leads to the first major insight. Design for additive is only half the game. The other half is design for inspection. AI can easily generate internal lattices, intricate channels, and organic shapes. Some of those shapes may even test well once or twice. But if the internal features are uninspectable, you are building a one-off sculpture, not a production engine. For strategy leaders, that flips the investment question. You are not buying printers. You are buying an evidence pipeline. Now consider what AI actually does well today in propulsion. The popular image is an autonomous system inventing a brand new engine. Reality is more practical and more valuable. Machine learning helps build fast approximations of expensive physics. It does surrogate modeling, reduced order modeling, and flow field reconstruction. It identifies systems from data and searches a design space efficiently. That means it can screen thousands of candidate geometries before you run full fidelity simulation and long before you do hot fire tests. But there is a sharp warning embedded in that same advantage. Surrogates are often accurate where you have data, and fragile where you do not. Propulsion lives on the edge cases. Combustion instability, shocks, flow separation, injector coupling, and rapid transients are exactly where you most want predictive power. They are also where models most often extrapolate. If your AI optimizer learns the smooth parts of the map, it may confidently drive you off a cliff at the boundary. That brings us to physics-informed neural networks and scientific machine learning more broadly. These methods try to embed governing equations into learning systems that can reduce the amount of data you need and constrain the model to physically plausible behaviors. Validity depends on the unglamorous details. Boundary conditions must be right. Training must cover the regime you will operate in. Uncertainty must be represented, not ignored, and every claim must be anchored to physical experiments. Physics-informed does not mean physics guaranteed. A second big insight follows. In propulsion, the most valuable AI is not the one that produces a pretty geometry. It is the one that comes with calibrated uncertainty, out-of-distribution warnings, and a disciplined validation plan. In other words, the most valuable AI behaves like a cautious engineer, not an eager designer. The materials story is equally instructive. Printed metals can approach aerospace-relevant properties, and that matters because engines are dominated by material limits. You are fighting heat flux, fatigue, creep, oxidation, and thermal cycling. One enabling milestone was the demonstration that high-strength aluminum alloys can be additively manufactured under controlled conditions, overcoming cracking barriers in selected cases. That result signals something broader. Alloy design and process design are coupled. You cannot treat material as fixed, and printing is merely a shaping tool. The process changes microstructure. Microstructure changes properties. Properties change allowable stress, lifetime, and safety margin. Yet process property relationships remain sensitive. Powder chemistry matters. Melt dynamics matter. Residual stress accumulates. Anisotropy appears, because printed parts can be stronger in one direction than another. Heat treatment can rescue or ruin performance. Surface finish and porosity can dominate fatigue life. Engines care about fatigue life. Engines also care about thermal conductivity, because cooling is life. So a third insight is that propulsion-grade additive manufacturing is a chemistry and metrology program, not just a mechanical one. Same file does not mean same part. If you cannot control powder lots, machine calibration, build parameters, and post-processing recipes, you cannot claim repeatability. And without repeatability, qualification becomes a moving target. Notice how these threads converge on the same requirement. You need a closed loop that connects design, simulation, manufacturing, inspection, and test. That loop has to be traceable. A modern propulsion organization should be able to answer a simple question after any anomaly. Which model version generated this geometry? Which training data supported that model? Which machine built the part? With which parameter set? Which powder lot was used? Which heat treatment was applied? What did non-destructive evaluation show? What did the hot fire data show? And what acceptance decision was made? By whom? Under which criteria? That end-to-end traceability is often called a digital thread. In this domain, it is not a buzzword. Without it, hot fire data becomes an anecdote, not a data set. Build logs become an archive, not a learning system. Failures become mysteries, not feedback. With it, you can do something powerful. You can run build, test, learn cycles that actually accumulate institutional knowledge and steadily expand the qualified design space. This is where time horizons start to separate. In the near horizon, from 2026 to 2050, the biggest wins are at the component level and small engines. You can redesign injectors, manifolds, and cooling channel segments. You can reduce part count and joining operations in places where inspection is solvable. Design cycles compress because AI screening reduces wasted simulation and test. Still, crewed missions and high-value payloads remain governed by conservative qualification and inspection standards. That conservatism is not cultural inertia. It is how you buy down catastrophic risk. In the mid-horizon, from 2050 to 2100, you can imagine propulsion factories that feel almost like living systems. Models propose changes. Additive machines build them. Sensors and non-destructive evaluation measure them. Test stands stress them. Data flows back into the qualified family of designs. Over time, the factory does not just make engines. It makes evidence, continuously. That is what allows faster iteration without gambling with safety. Longer horizons depend on whether standards and inspection methods can travel off-Earth. In space, manufacturing is often described as printing parts from local material. For high-performance engines, that is far beyond routine reality. Engines demand material pedigree, tight process control, and high-confidence inspection. If you cannot guarantee those in a lunar or asteroid environment, you may still print simpler hardware, but not your most demanding propulsion systems. The glamorous vision is plausible only if the boring infrastructure comes along, including calibration, contamination control, and certification language that works across sites. All of this clarifies the risk envelope. There are two classic failure modes to watch. One is unvalidated surrogate extrapolation, when a model is used outside its training coverage. The other is hidden additive defects, especially in internal geometries you cannot adequately inspect. A third, quieter risk is brittle record keeping. If your digital thread cannot survive audits, personnel turnover, and supplier churn, your qualification posture erodes over time. So what should capital allocation leaders do differently? Treat AI-designed, additively manufactured propulsion as an integrated stack investment. You need design software, powder control, machine qualification, post-processing, non-destructive evaluation, test infrastructure, and data governance. Buying a printer without the rest is like buying a jet engine without a fuel system, a sensor suite, or a maintenance manual. Staffing follows the same logic. You need propulsion engineers? Yes. You also need material scientists, additive process engineers, non-destructive evaluation experts, certification specialists, and ML for fluid mechanics talent. Most of all, you need people who can translate between these groups, because the interfaces are where projects die. A final governance point matters for anyone who will sign off on risk. Never allow an AI-generated internal geometry to reach manufacturing unless inspection feasibility and acceptance criteria are defined in advance. Otherwise, you are incentivizing your optimizer to exploit blind spots, both in simulation and in measurement. That is not malicious. It is what optimizers do. The memorable line is simple. In AI-designed propulsion, performance is optional, but evidence is mandatory.